Okay, so previously we looked at how a variety of nucleophiles can react with ketones and aldehydes. Specifically, we looked at oxygen nucleophiles and nitrogen nucleophiles. What I want to do next is jump into sulfur nucleophiles and hydrogen nucleophiles. So let's start with sulfur nucleophiles. And luckily, this is pretty straightforward. In many ways, it's identical to what we've saw with oxygen nucleophiles, considering sulfur's in the same row. And just like with oxygen nucleophiles, you can have two equivalents of a thiol under acidic conditions form something that looks like a ketal, where both of those thiols can add in, and you can kick off water as a byproduct. This is referred to as a thioketal. In this case, it happens a lot more readily because sulfur is an even better nucleophile than oxygen because it's much less electronegative and it's much more polarizable. Conversely, another method we can use is to use a molecule that has two different thiol groups on it. And just like we saw with oxygen, if you do this, you can essentially protect a ketone and make a cyclic ring system out of it. Again, you're going to kick off water as a leaving group, and this is referred to as a cyclic thioketal. It's usually not used for protecting purposes, primarily because the starting material is so stinky, but it is useful for another trick. So I'll show you this other trick. Let me make this black as well. So a cool trick is to first react your ketone or your aldehyde with your thiol and form your cyclic thioketal. So we'll go ahead and do this. Should work pretty easily. And then next, what you can do is treat it with something called Raney nickel. So R-A-N-E-Y, and then nickel, N-I for the element symbol. And when you do that, you can completely get rid of the sulfur groups, and you can install two new hydrogens there. So this looks a lot like the reduction chemistry that we've seen before. But before we start comparing and contrasting those, I did want to talk about what Raney nickel is. So Raney nickel is a spongy nickel aluminum alloy. So it's a combination of nickel the metal and aluminum the metal, and it has hydrogen gas absorbed. And the good thing about this is we don't need to know the mechanism for this. This reaction, if you're curious, actually has a name. It's called the Mozingo Reduction. I don't think our textbook actually names this reaction, but it is one that's used, I would say, fairly commonly in organic chemistry. All right, so let's compare and contrast all of these reduction techniques. Because really, we've got a bunch that look similar. Okay, so let's do the first one that we saw a while ago, actually, where we have a ketone, and we can treat this with a zinc mercury amalgam and hydrochloric acid. This is the Clemmensen reduction. And in the Clemmensen reduction, we saw that we could, again, get rid of that CO double bond. So this is pretty nice. And we saw previously in this chapter another method that's pretty similar. This time I'm just going to use a non-aromatic ketone, where you can first treat it with hydrazine. Let me make this line a little bit longer. You can use catalytic acid and make your imine by driving off water. And remember that this acid is usually controlled pretty carefully by using buffered conditions. All right, in the second step, we treat this with NaOH, sodium hydroxide. We treat it with water, and then we heat it. And when we do this, we can again get rid of this CO double bond in our starting material. So it looks pretty similar. All right, and let's take a look at this last one. This last one is that Mozingo reduction that we just looked at. And just like before, it's going to be 2 steps. First step is forming our cyclic thioketal. So we'll label that and we'll drive off water. And then second step is that Raney nickel. And this reaction works just like the Wolff-Kishner reduction right above it. In fact, it's in many ways interchangeable. All right, so let's talk about the pros and cons for each of these. So this first one, the Clemmensen reduction up here, this works best for aromatic ketones, meaning the ketone should be attached to an aromatic ring, right? So let's make a note. And I'm going to call this an aryl ketone to indicate that we must have this aromatic group coming off that ketone. All right, these other ones work with any ketone. So they're a bit more versatile. And let's take a look at some other situations we should pay attention to. This one up here, we're using acid. So if you have an acid-sensitive functional group, this is going to be a big problem. In the second one, we use strong base. So if you have a base-sensitive functional group, that one will be a problem. And then on the more pragmatic side for this bottom one, this stuff is super stinky. It is really like overwhelmingly powerful. Once it gets in your clothes, you'll smell it in your basement or in your washing machine for a couple of days. So it's kind of pick your route. In some ways, this first one is the least desirable because you're using mercury, which is pretty nasty. The second one, you're using hydrazine, which is pretty nasty. And this one, you're using a super stinky reagent. So you have to be kind of careful with which method you're picking and choosing it for the right reasons. All right. So let's jump into hydrogen nucleophiles really quick. And the hydrogen nucleophiles are going to use reagents that you're pretty familiar with. So this should be a pretty quick review. But the idea is, how can we add some sort of hydrogen into here? And you can imagine if we add a hydrogen in, I'm just going to make this a red hydrogen right here, we would end up with an alcohol. Well, we actually have a few different tools to do this. The first one is lithium aluminum hydride, LiAlH4, followed by an aqueous workup. That would install a hydride, and a hydride in this case is going to be the hydrogen and its electrons, which means it's nucleophilic. And then the second option is to use sodium borohydride and methanol. If you remember, this sodium borohydride is a lot more gentle. You don't need to do 2 separate steps. The alcohol, which is used as your solvent, can be used to protonate the final product. So this is a pretty straightforward reaction. This also works with ketones as well. So let's make a note of this. The interesting thing with this is when you look at each of these, they're basically a source of H-. And H-, if you remember, is hydride. Hydride isn't soluble, meaning it doesn't float around freely in solution, but these more act as delivery agents for hydride. So they'll deliver an H- to that carbonyl, and then the reduction reaction can proceed. All right, so we'll stop right there, and then when we come back, we'll take a look at carbon nucleophiles.